Hi, I've had a request from a learner to talk about as a review, the 7 common tools of total quality management TQM. So what we're going to look at here then is these 7 tools here. Something which is called a check sheet, which is a tool that we use to be able to capture information. Second, a Pareto chart. And in a Pareto chart, what that allows us to do is to be able to rank the occurrences of the events that we're measuring. A cause and effect chart. Now, a cause and effect chart is also called a 5Y chart, an Ishikawa chart, Fishbone chart. It's a tool to start brainstorming the different causes to try to get to the root cause of an issue. A flowchart, which is a visual representation of what the process steps are and the decisions that have to be made in the process. A histogram, which is a graph of the frequency of occurrence of different types of measurements that we're taking. And then a control chart, which is a measurement tool that allows us to see if a process is remaining in control or not. And then finally, a scatter diagram, which allows us to do some visual analysis to see what the trends are in the process here. So these are the 7 that we're going to look at. So let's go in and look at these 7 here. We'll open up a new page and we'll start with the check sheet first. What a check sheet is, as I mentioned, a way to collect data. And a most common way that you'll probably see this is you'll have a issue on the factory floor with a dimension or a measurement or a characteristic, and or it could be an existing part or a new part. Call up the engineer. The engineer looks at it, works with it, and then he or she turns around and says, not 100% sure what's going on, but let's collect some data. And so they'll say, hey, for the next couple of days as you're making it, will you keep track of what happens for issues and how often? So essentially what we're doing, however we're doing it, is we're putting together some type of manual document where we're going to keep track on that piece of paper the issue that came up and the number of times it came up. So the first problem we run into might be a bent part. It happened once, and then we went to another part that had a dent in it. When we ran across, we had we put another fence post there. We came back and hit 2 more in a row down the line on bent, and then maybe a crack might have been the third thing that happened twice in a row. So we're keeping track of this, and we're trying to collect the incidents and the number of times that it occurs. So a check sheet is a way to collect data so we can see what things are happening and how often. And it's not unheard of that we'll also look at this over time as well. So this could be today, and then tomorrow we're going to keep track again, and we'll do this over time as well. A second tool that we'll use that comes right after this then is going to be the Pareto chart. And a Pareto chart takes the events and ranks them visually on a graph from the highest incidence to lowest incidence. So if we take the same situation on a graph, we had, what was it here? 8 instances of bent. So this would be bent. And we'd have 1, 2, 3, 4, 5, 6, 7, 8 times. Second biggest one was cracked, and so crack was 3 times. And then the dent, in this case, was twice. And so where Pareto comes from Pareto's law, the 80-20 rule, is we rank all the items from highest to lowest in terms of quantity. And the argument is that 20% of the items makes up 80% of whatever we're measuring. So there's a significant few and a trivial many items. In other words, bent is the most important. So that's the one we're going to work on first to problem solve. And then we'll move down to crack parts and then down to dent parts. So what Pareto allows us to do is take the data that we collected and then be able to show it ranked from highest to lowest so we can prioritize what we're going to fix. And typically that's done from highest to lowest. So the third tool that we run into, the cause and effect chart, or Ishikawa chart, Fishbone chart, 5Y chart, then takes that problem of parts being bent, okay, and then it starts looking at it in terms of why it's happening. So what I'm drawing here is I'm going to make 6 veins or wings coming off of this, because what we're going to start with on the first Y is asking, well, why did things bend? And then we're going to start brainstorming why. But fundamentally, what we end up doing when we end up looking at it is we categorize it or group to make life a little easier for ourselves. So we group things by method, by material, could also be by measurement, could be by environment, could also be, when we look at it, by manpower or machines. So we say, well, why did the part bend? Well, it could be because the material is soft. So we would have a little line coming off the material that would say soft. And someone else may say, well, the method we use has too much pressure on it. So then we put in here too much pressure. And we keep brainstorming. And so we keep adding these veins as we go through it. But then we also go a next level deep. So if we look at why did the part bend? Because the material is soft. Then we'd say, well, why is the material soft? And it would branch off to that to say maybe we've got a bad specification. And then we'd add again, well, why do we have the bad specification? Maybe because nobody understands what the specification is. The idea is we continue to ask why on all these and branch off enough times that at some point we're going to see a couple things happen. One, we just may run out the string or not be able to go any further on a path, which means it's something that's outside of our control at that point. That's a dead end. Or we start seeing the consistent themes coming up. Maybe it's going to be bad specification here and bad specification on the machine down here. And the environment could be we're rushed so we can't come up with the specification. When we start seeing the same things pop up, then that raises the flag for investigation to say, hey, the effect is a bent part. A potential starting point for a cause is going to be this bad specification that we're seeing pop up all over the place. And that's what we're going to tackle first. A fourth tool that we'd run into, make a new page here, is going to be a flowchart. And a flowchart is just a visual representation of a process. So we're going to start right here, whatever start is. And the first step in the process might be to, let's just say cut to length. So we've got a metal rod that we're going to cut to 1 inch length. And then after that, it's cut to length. The next step in the process is going to be to take off the burr. The burr is the little rough edges that are on the edge of the piece of metal that's cut. And then the third step might be to then coat it with some type of lubricant, coat with lubricant. And then I'm just going to come down here. Fourth step in the process is actually going to be to now inspect the part. So we look at the part to inspect it. And then the next step in the process is decide, and we use a diamond for that, is the part in spec? Yes or no? If yes, then the final step might be box up part. Put it in the box, get ready to ship it to the customer. If no, then it might be to redo the part, or some kind of final inspection, or touch up the part or whatever. And then we're going to come back to inspection and go through an inspection again, where it's either going to stay in this loop or it's going to go off and finally be boxed up. But it's a visual representation of a set of steps or processes, which are the squares or rectangles, and then the diamonds are the decisions. And so it gives us a chance to see in one big picture what the process looks like. Now we're going to go look at a histogram, and a histogram gives us a measurement of how often the occurrence occurs. So you could come back up to the beginning here and look at the Pareto chart and say, well, isn't that a histogram here? Absolutely. A histogram is a representation of how many times, in this case 8, this event occurs here. It becomes a Pareto when we sort it and rank it from highest to lowest. But a histogram, we might be measuring the length of a part to see how it's doing. So here's a graph. We've got a part that's supposed to be 1 inch in length. We grab 28 parts. We measure the first one and it's 1 inch. We measure the second one, it's 1 inch. We measure the next part, it's 1.1 inch. We measure another one, it's 1.4 inches. Another part after that is 0.9 inches. And then we keep going, measuring these parts, and we're trying to get a sense of what the makeup is of the parts that we're seeing here. So what we can get out of it is something like this that says, hey, it looks like a normal distribution. The bell curve and a normal distribution means it's a process that's under control and behaving normally with no outside influences. But it can also tell us this, is we may take a sample that looks like this. And we go, ooh, it looks like half of a normal distribution. How's that possible? And normally it shouldn't be. We should expect to see the other half of the normal distribution. And so with learning and knowledge, what we come to realize is, the only reason this happens over here where there's no parts is we possibly could have sorted out parts that were on the low side because the customer said they did not want parts less than 1 inch. So as we learn about how the part is made and then we graph it here via a histogram, the result, the picture, can give us an indication or some potential insight into potentially what's going on. In this case, they had to sort out parts. Now, is that good or bad? We don't know. We've got to see what the requirement is on the part. But it's a visual representation of the number of occurrences of a part, or of a feature or an event or a characteristic. Next tool is a control chart. Control chart has us taking a sample of parts. Let's say we grab 32 parts out of a box of 10,000 fasteners, and we measure the length, and we figure out the average, the mathematical mean, and what we do is we plot that over time. So this is time down here. We plot what the length of that part is. Now what we also calculate, and so the sample of 32 pieces might be the average is 1.05 inches. Now what goes with a control chart is something called a upper control limit, UCL, and a lower control limit. This is saying statistically, if the process is behaving normally, under control, we would expect to measure parts that are within the range on the upper end and the lower end. Control limit meaning the edges of the normal range of the process. And so perhaps that could be, it operates normally by making parts between 0.98 inches and 1.12 inch. And what a control chart says is once we calculate that, then we're going to continue to measure samples of 32 over the length of the production run, calculate the mathematical average, and we're going to plot it here over time. Okay? The idea being, is that as long as our sample stays within the upper and lower control limit, process is behaving normally. So this is the range of normal variation. And if we get a measurement outside of this range of normal variation, maybe up on top here, we would stop the process, isolate the parts, call the engineer down, have him or her look at it, and decide if that was just a one-off and we should keep running, it was just an odd situation, or is it tipping us off to something else? And if it does, then they might have us isolate all these parts we built before and set them aside, and then they'd ask us to continue running parts, and maybe they'd stay in normal again. And then they'd say, okay, go ahead and ship everything. But if it happened again, we got another part outside the control limits, then we'd have to stop the process and figure out what's going on and fix the process. The last tool then is called the scatter diagram. What a scatter diagram does it allows us to graph two variables, maybe, I don't know, something like temperature and humidity. And we grab a sample and we see when we get this temp, we see this level of humidity. And when we go to a higher temp, things are getting hotter, so we see a lower humidity. And so we measure samples over time of the temperature and the humidity. And another one's up here, another one's down here, another one gets to be up on top, another one down here, another one over here, down here, so on and so forth over time. And then we use, if you're in Excel has a feature, it's called the best fit line. We can calculate manually or visually, but we can kind of see a pattern appearing here. And this best fit line is the line that fits literally the best with the minimal variation between the data points and this average right here. And so what this allows us to do with the scatter diagram, we're able to diagram a scattered set of data like we just did. And now we can see what this line is of best fit. Okay. And it allows us to predict. So if this is, maybe we're in a greenhouse and we come inside the door and the temperature is 82 degrees, we would expect to see humidity about right here, whatever that is. What that allows us to do is not only understand the process better, how variables are related to each other, but if we want an increase or decrease in humidity now, we can also predict then from this to say, well, if I want an increase of humidity from A to B, for this greenhouse, I need it to be up to B, then that says, well, we got to take the temperature down to a point right here, where if I go up, it lands about where that humidity is. So that allows us not only to understand, but to predict what the other result might be based on the first variable, as well as control the process to be more efficient. So these are the 7 tools that we're talking about that are commonly used in total quality management.